Here we have the function a of x, and we want to find the intervals of increase and decrease and the local maxima and minima, and any intervals where a is concave up and concave down. So, in order to do this, we're first going to start by finding the first derivative. So we've got a prime of x, and we see we have a product rule, so we do first times the derivative of the second. Okay, I'm going to write that. I'll just put it over here to this side. I'm going to write it as a 1/2 power so I can think about the power rule. So we're going to do power out in front, decrease the power by 1, and then the chain rule is multiplied by the derivative of what's inside, but the derivative of what's inside is a 1, so we don't need to worry about that. We did first times the derivative of the second plus the second, which is x plus 5 to the 1/2 times the derivative of the first, and that's just 1. So here we have the derivative, and let's actually write it back in radical form so we can look at it and see what we're going to do to solve it. 1/2 x, and that's going to be over square root of x plus 5 because it had that negative exponent on it, plus, and this next term is square root of x plus 5. So if we're wanting to look at that to find critical numbers, we're going to want to combine those and get them under one fraction. So let's get a common denominator. This needs a square root of x plus 5, and whatever we do to the bottom, we got to do the top, so that would make it squared, and that will actually undo the radical. And now I'm going to rewrite this 1/2 by putting the 2 down there. Rather than have a fraction in the numerator, we're just going to make it down there. So we also need a 2 on top and bottom here. And that 2 is going to get distributed to this x plus 5. So let's rewrite what we've got over here. And we've got a common denominator of 2 square root of x plus 5. And the numerator, we've got x plus, let's take this 2 and distribute it. Remember, this radical's gone and the squared's gone. So this is going to be 2x plus 10. So if I just combine those x's, 3x plus 10 over 2 square root of x plus 5. All right, that's my first derivative. So now let's find any critical numbers. One of the things we didn't talk about that we should have was back in our original function, we've got, let's look at the domain. We've got a domain restriction because we can't take the square root of a negative, so our domain, I'm going to put it over at the top right corner, our domain is going to be from -5, including -5, because it could equal -5, and then the function would just be 0, and then to infinity. Okay, so within our domain I'm looking, and we do have it undefined at -5 for the derivative. So I'm going to make a number line with the sign chart. So this is where our domain starts, and our derivative is undefined there, and then it goes to infinity. There's another place we have a critical number because we want to figure out where this equals 0. Well, when the numerator equals 0, the fraction equals 0. So 3x plus 10 equals 0. Let's move the 10 to the other side, get rid of that 3, so it's -10 thirds. Now -10 thirds is about -3.33, so it's going to be to the right of -5. So here's -10 thirds, and that's when it equals 0. So our function doesn't exist to the left of -5, so we just have two intervals to consider between -5 and -10 thirds, and then to the right of 10 thirds. So let's go ahead and plug in a value between these. Let's try -4 because we knew -10 thirds is -3 point something. So -4 is between them. And if we tried -4 in our derivative, the denominator is going to be positive. And -4 times 3 is -12. So that's going to be more negative than the plus 10, so the numerator is going to be negative. So right in between here is going to be negative. And now let's try, let's just put in 0. So 0, the denominator is positive, 0, the numerator is also positive, and so it's positive there. Okay, so what did we find out? We've got our sign pattern, and we found out that it's decreasing from -5 to -10/3, and then it's going to be increasing from -10/3 to infinity. And so at -10/3 it was decreasing, then it's increasing, and so that's going to be a local min. So we've got a min at -10/3, and we need to plug -10/3 in the original function. All right, so I'll just plug it in right here. So I'm going to put in -10/3. So we've got -10/3 square root of -10/3 plus 5. And we can work underneath the radical to get a common denominator. So let's do that. So let's make that into thirds. So that will be 15/3 minus 10/3, but it's underneath the square root. So the y value is going to be -10/3 square root of 5. So there's our minimum. So we found the increase and decrease. There is no local maxima, and we found the local minimum right there. And now if we are working to find the concavity, we need a second derivative, so we're going to go right here. I'm going to box it in. That was our simplified first derivative. So we're going to need to do a quotient rule. So we are going to take the bottom 2 square root of x plus 5. Actually, let me write down what I'm doing. I'm taking the second derivative. So I got 2 square root of x plus 5, which is the bottom, times the derivative of the top, which is 3, minus the top, which is 3x plus 10, times the derivative of the bottom. So we know that bottom is just like I've written up here in the top right corner. It was that x plus 5 to the 1/2. So the power comes out in front, and there was actually a 2 out there, so they'll cancel and then decrease the power by 1. So this is going to be x plus 5 to the -1/2. I'm then thinking of the chain rule, but it's a 1. So we're in the middle of the quotient rule. There's our bottom times the derivative of the top minus top times the derivative of the bottom. So now it's all over the bottom, which was 2 square roots of x plus 5 squared. Okay, so let's see what we can do to simplify things or to be able to express this. I'm going to express it in radical form without the negative exponent as well. So I'll combine this 3 and this 2. So I've got 6 square root of x plus 5, and then I have minus 3x plus 10 over square root of x plus 5. And then down here in the denominator, I've got 4 times, when we square the square root, that'll cancel, so just be x plus 5. So this is the second derivative, but we've kind of got a fraction within a fraction. And so what we're going to do is we are going to clear this of fractions. So the numerator, we're going to multiply top and bottom of this then by square root of x plus 5. And we're going to do the same thing down here, square root of x plus 5. So when I multiply it to this one, that will get rid of the square root sign. So I'm going to put it over here down at the bottom in red so we can see it. So we got 6. It's going to be x plus 5 because it was square root of x plus 5 times square root of x plus 5, which got rid of the square root sign. And then it's going to be minus, and the square root of x plus 5 on the top will cancel the denominator that's under the 3x plus 10. So it's just going to leave us the 3x plus 10. And then down in the denominator, we've got an x plus 5, and that, think of that as like to the 1, which is like 2 halves. And then this square root of x plus 5 is x to the 1/2, so they'll combine to have it 4 and then x plus 5 to the 3 halves. Okay, so one last step to simplify. I'm going to distribute these through and make sure this negative gets to these guys, and then I'm going to combine like terms. So 6x plus 30, I'm just going to write it above because there's not any room. Okay, and then so 6x, this negative will go to the 3x, and 6x minus 3x is 3x. 30 minus 10, which is plus 20, and then that's all over 4, and then x plus 5 to the 3 halves. So that's my second derivative. And now if I'm looking for intervals for concavity, I need to figure out where that's undefined and also where that would equal 0. So first of all, it's going to be undefined looking at the denominator when we have negative 5. And that's where the domain starts again. So negative 5 undefined. And then taking the numerator and figuring out when the numerator equals 0, that would be when 3x equals negative 20 or x equals negative 20 thirds. So the other spot would be negative 20 thirds, but wait, negative 20 thirds, when you look at negative 20 thirds, you could put it in the calculator or you could just approximate it, but that's going to be negative 6 and 2/3, and that's outside of our domain because the smallest we can use is negative 5. So we don't have any other critical numbers, just this end here, so we just need to test somewhere. Well, let's test 0 because that's the easiest. And if I put that in, the denominator and the numerator are both going to be positive. So this tells me that the second derivative is positive everywhere on the domain of this function. So that tells me it is concave up from negative 5 to infinity. Now let's look at the graph of this equation and see how we did. Okay, here is the graph. Notice that it starts at negative 5, and anything to the left of negative 5 is not in the graph. So its domain was negative 5 to infinity, and we found out that there was a local minimum at x equal negative 10 thirds. Well, negative 10 thirds, if you divide that, is negative 3.33 whatever. So here's our local minimum that we found. And we found out that the y value was, we had negative 10 thirds and times the square root of 5 over square root of 3. And if you put that in the calculator, we would get this value. And then we also found that there was no local maxes, and we also found that it was concave up everywhere. So looking at this graph, that confirms the things that we found. We also found it was decreasing from negative 5 to negative 10 thirds. So there's our part where it was decreasing. We found it was increasing from negative 10 thirds to infinity. And all of these things confirm what we found using calculus.